So I'm not sure I'm the world leading expert on this. There's a bunch of others that could have given this lecture equally well, if not better. Anyway, yeah, you introduced the topic, so let's jump into it. And I try to mix up a few of the perhaps newer developments and newer insights, in particular when it comes to arc and backarc hosted hydrothermal systems, with some of the more basic things that some of you will probably already know, but others in the audience may learn some of the physical chemical fundamentals of these submarine hydrothermal systems. So I really like this slide from McTivie's paper from Oceanus. And what we see here is basically the conceptual model of high temperature hydrothermal vents in the deep sea. It starts with seawater that gets entrained into the crust and undergoes heating and a plethora of reactions that change the composition of seawater radically. So there is a lot of water rock reactions going on in the system in different places, in the recharge zone, so on the way down, in the reaction zone where the temperatures peak, and then the reactions continue when the fluids come up. And in the shallowest part of the systems, there's also continued water rock reactions between these upcoming fluids, between seawater that gets entrained, and between precipitates that formed there in earlier stages. So we'll be talking about water rock reactions. We'll also be talking about phase separation, because this is what you see here. The phase separation and the segregation of these phase separated fluids is also an important component in these systems. And in particular, in the arc and backarc systems, as we'll see, the magmatic degassing also influences the chemical reactions in these systems a great deal. And finally, a fourth process I would like to address is what happens when the cold seawater gets entrained into the system. There's chemical reactions, mineral precipitation, dissolution. This is where microbial activity is really boosted. So I'll be talking about this a little bit. So it's a very rich topic, and you could fill an entire series of lectures with it. So I tried to boil it down to basically talking about these four processes that we just looked at: water rock interaction, phase separation, magma degassing, and then there's subseafloor entrainment and mixing of seawater. And I tried to break it down into how these four processes affect different properties of the fluid in terms of salt, gas, and metals. And we'll start with salt and gas. And then we'll talk about metals last, because the understanding what the metals do is really complex. And it requires us to basically keep track of all of these four things in concert, and how we can go about doing that. That will be the final part of this lecture. So here's the content. After giving this a brief introduction, we'll be looking at some examples from the published literature where scientists have shown how, in principle, we can use fluid composition to tell us about subseafloor processes. I'll then introduce a fairly new vent fluid database that Alexander Diehl put together, the MAHUS database, and we'll use that to look at phase separation, water rock reactions, and magma degassing. I'll then, being a petrologist, of course, I like phase diagrams. So I'll show some of these phase diagrams because I think they are very helpful tools in linking the vent fluid compositions and the seafloor massive sulfide deposit compositions. And then we'll wrap it up with a case study. We'll be looking at some of these vent sites in the Manus Basin in Papua New Guinea. And we'll be talking about how the full complexity of the vent fluid and sulfide composition can be brought to bear in trying to understand the chemical reactions and related mass transfers in these systems. Okay, so I start with a historical perspective, and this is about phase separation, which was observed directly by seafloor sampling, and this happened in the course of time series sampling at the East Pacific Rise 9 degrees north between the years of 1991 and 2008. And following a volcanic eruption in 91, the first fluids that were sampled at the hydrothermal sites that started to develop right where the eruption took place. What was sampled in the early years, in the early 1990s and mid 1990s, was dominated by vapor. You can see this here. This is chlorine, and you see the chlorine concentrations were very low. And then after a number of years, they came up. So vapor-rich fluid was venting early, and then it turned into a briny fluid later on. You can see how iron, this is iron here, is very tightly coupled to chlorine because the iron, in order to be dissolved, it needs the fluid to be briny because it forms complexes with the chloride anions. And then you see that H2S, so hydrogen sulfide, which is a dissolved gas, shows a trend that is opposite to that of chlorine. Okay, so very high H2S concentrations early on, and then lower H2S concentrations later on when the fluid was briny. So this was, you know, it's always nice if you see these processes directly expressed in nature, and you can do this time series sampling and study the evolution of these hydrothermal systems. So that's there was a bunch of wonderful studies that came out from the RIDGE and RIDGE 2000 programs. This is another classic paper by McTivey, which shows very nicely how we can learn from looking at the composition of hydrothermal fluids about subseafloor processes. This is from the TAG hydrothermal mound. And I know this is a busy slide. I'll just try to guide you through it. What we are looking at here is a table from the paper, and we are looking at the differences between the black smoker fluids here that vent in the center of the sulfide mound and are hot, and the white smoker fluids, which went from a more peripheral part of the mound, and they are substantially colder. So we are looking at the compositional difference in terms of pH, and we see the white smoker fluids are lower in pH. I extracted two of the crucial reactions that are part of this reaction network that is going on inside the mound. And we'll see that all these differences in the compositions between the black and white smoker fluids can be explained by invoking these reactions, which are the precipitation of pyrite, which lowers the pH, explaining this difference. It produces hydrogen, which we see here. Hydrogen in the white smoker fluids is much higher than in the black smoker fluid. It removes iron, and we see that here. Iron is lower in the white smoker fluid than in the black smoker fluid. And then it also consumes H2S, and again, we see that in the data. And what happens with the released protons here is they attack sphalerite that was deposited earlier inside the mound, and that causes a remobilization, and that part of that sphalerite gets dissolved, and you see that in the zinc contents here, which are greatly elevated in the white smoker fluids. Okay, so this is a wonderful testament of the power that the compositional differences of fluids that come from different parts of these seafloor hydrothermal systems have in terms of telling you about the reactions going on in the subseafloor. I'm not going to talk about this, but this will be a wonderful topic for another lecture, perhaps, is how we can use fluids to study microbial processes. And just briefly mentioning that there's two principal ways to go about this. First is purely observational, just doing measurements. And this is from a paper that Karen van Dam and Marv Lilly published in 2004. It's actually a book chapter of one of these AGU monographs. Anyway, what they observed at the EPR 9 North is that these diffuse fluids that are fairly low temperature, they have much more methane than you would expect if these fluids were simple mixtures between seawater and a hydrothermal, pure hydrothermal end member fluid that would be somewhere over here at 0 magnesium. Okay, so this is telling us something about microbial metabolism. In this case, it's methanogenesis. So microbes make methane by reducing CO2 with the help of hydrogen. You can also use end member hydrothermal vent fluid compositions and do thermodynamic modeling to predict which microbial metabolic strategies might be most successful where in the system, and how much cumulative autotrophic biomass production that may drive. Okay, and here's a fourth example. It's actually not from seafloor studies, but it's from studying fumarole gases in volcanic arcs. And that's a line of study that was pioneered by Werner Gegenbach. And this is from a recent Elements paper, which shows very nicely that in addition to water rock reactions that we have in geothermal systems on land, in these seafloor hydrothermal systems, there is this magmatic hydrothermal branch here, where basically the redox of the system, the sulfidation state of the system, is controlled by the influx of volcanic gases. And wherever that happens, conditions are much more oxidizing than where all you have is water and rocks. And this causes this, what's termed the clash of redox buffers in these type of systems. And this, in a nutshell, causes some of the complexity that we see in arc and backarc hydrothermal systems that I'll be talking about next. So here I'm introducing now the Manus database that Alexander Diehl put together. He's a postdoc in Bremen. And you can see it has almost 3,400 entries. And I just extracted some of that data to make these plots to explain you how we use vent fluid compositional data. Usually what we do is we measure the compositions, of course, of the major minor trace elements dissolved, and then we start plotting things up, usually against magnesium. And what we expect to find, and this is what you see in almost all mid-ocean rich vent fluids that were ever sampled, is a tight correlation between magnesium and sulfate. And this is due to what you saw in McTivy's slide, the first one I showed. It's basically you're precipitating chloride and anhydride in the downflow and reaction zone. And that co-precipitation causes this co-variation of sulfate and magnesium. And they basically, the hydrothermal end member fluid sits down here, where sulfate and magnesium are basically close to zero. Okay, so, but this is only part of the picture, because you see there's some data points that do not plot on this trend that most people, most samples define. And instead they show an excess of sulfate, which tells us that the anhydride dissolution takes place in the subseafloor. And then what you do next is you look at calcium and strontium and hope to see the same excess, which you usually do. And then there's another subset of fluids that shows actually an excess of magnesium or a lack of sulfate, and this can point to anhydrite precipitation. Okay, you see where these axes end at 30 and 55 here. So actually, when you look at the full picture, you see that in the arcs and backarcs, we find another class of fluid samples that do not fall on this trend at all. And this is, you see here, and vents that have fluids with those type of compositions are heavily affected by degassing of sulfur dioxide, which when it meets with water disproportionates and forms H2S and native sulfur, and also sulfuric acid, which of course dissociates and make these fluid high in sulfate and also highly acidic. That's why we call these fluids acid sulfate fluids. Okay. And then you see another trend, and this is something we actually found out existed only a few years ago. We sampled fluids in the Kermadec arc and measured magnesium on board and got these high numbers and thought, well, you know, there's probably something wrong with the method. But it turned out that these magnesium excesses are real and that they are correlated with sulfate excesses. And one way to explain this data is by caminite dissolution. Caminite is a hydrous magnesium sulfate that forms when you heat seawater. Okay, but this really hasn't been, I don't know, the verdict is still out if this is really the explanation for it. It's the best we could come up with at the time. Okay, so quickly, we'll look at the Marhus database plots. And we look at chlorine versus sodium and see a beautiful correlation. Seawater is here, and you see that roughly the trend you see follows that ratio of chlorine and sodium that we have in seawater. But there are deviations, and you see that most of the briny fluids here actually show less sodium that you would expect. Some of the vapor fluids, some of the less briny fluids also show this. But some of these data that plot down here from the arc and backarc systems actually can be explained by the addition of magmatic HCl. And then there's this other trend here that points to, you see 800 is right here. So stoichiometrically, if you dissolve halide, you get this kind of trend. Okay. So this, of course, is telling us about phase separation. So I have this little thing in here to explain those of you who aren't sure what that really means, phase separation, what it is. And you see the PT diagram here. This is a schematic path of seawater. It comes in cold. This is the recharge zone, and then it gets heated and turns buoyant at some point in time. And most of these fluids, by their composition, they tell us that they cross what we call the critical curve, which is what you have in a system where you have next to water also salt. And now this is a TX section where we see the solvus lines that are pressure dependent, and focusing in on this, if you ask yourself, well, where does seawater plot? It plots here at 3.58% sodium chloride. So if you heat seawater, what will happen is at 300 bars, it will be touching the solvus. And if you keep heating, and in the example, I'm heating it to 420 degrees C, you see that now a single phase is no longer stable. And in fact, you get phase separation, and make two phases. One has a lot of salt and one has very little salt. And you can actually just read the salt contents of the x-axis here. And then you can use the Lever's rule to calculate how much vapor-like and how much briny fluids did we make. You may ask yourself, well, what happens if we take one of these fluids, say the brine, and have it come up a little bit while it undergoes cooling? This is what's going to happen, right? If you have the brine come up 500 meters and cool it by 10 degrees centigrade, you move here in the phase diagram. And at 250 bar, then you're dealing with a new solvus, this one. And you see what happens is the brine got brinier and the vapor-rich fluid got less briny. So this is what these fluids will do at these, when you superheat seawater, which is commonly taking place in these systems. Okay, and then, we have this mixing with entrained seawater in the shallow subseafloor, and that will just have the salt level and temperature drop in the fluids, but they usually remain in the single phase field from then on. Okay, so this explains this variabilities that we saw in the salt department, right? It's mainly phase separation, and then there's also water rock reaction. Let's talk about gas next. And the first thing we need to know is that the gas that comes off a magma, not all the gas comes out of the magma at the same time. And again, this is from one of Werner Giggenbach's papers that shows very nicely that if you degas a basalt, first the CO2 comes out, then the water comes out, and then the sulfur comes out last. Also, of course, a magma is not equal to magma. It depends on if you are on a mid-ocean ridge or in an arc. In arcs, you're dealing with hydrous magma, so you have a lot more water degassing much earlier than in on a mid-ocean ridge hosted system where the dry mantle, of course, can't make hydrous magma, so there's no vapor, just CO2, mainly CO2 coming off the crystallizing magma reservoir, the heat of which drives these systems. The second thing you need to be aware of is that the gas speciation is very strongly pressure dependent. And this is shown in this diagram here. Here you have pressure and depth in the water column. And this is from this paper here. And the magma type is tholeite. And you see that deep you get CO2 degassing. You need a shallow depth to have the water come out of the magma. And please note that the fumarole gases that we sample on land, where the pressure is 0.1 megapascal, it's always dominated by sulfur dioxide. Just look at sulfur dioxide here and hydrogen sulfide. So at low pressures, all the fumarole gases will be dominated by sulfur dioxide, but you don't have to go very deep. See, just 100, 1,000 meter water depth to have the sulfur speciation in the magmatic gas be completely different. So we can expect actually to have highly variable sulfur dioxide H2S ratios in the magmatic gas that comes into these seafloor hydrothermal systems. Talking about gas, it's imperative to use gas type fluid samplers. We like to use the one that Jeff Seawald built 20 years ago. And here you see it in action, and you can then retrieve the fluid that is kept under seafloor pressure. All the degassing takes place in a gas-tight syringe, so it's a closed system, and then you can use a GC that you bring on board to measure these gas species, and the CO2 you can measure later in the lab. So again, questioning the MAHUS database, looking at CO2, and you can see here CO2 versus water depth. Actually, the backarc and arc systems have much more gas. You know, we were, of course, expecting to have more sulfur and water, but just CO2 also, it's much gassier in the arcs and backarcs, indicating that there is a generally higher gas flux in these systems. This is CO2 versus sulfate now. And here we see that the degassing can be highly variable. It can be dominated by CO2, like in these systems, or it can be dominated by SO2, like in these systems that have these astronomical sulfate concentrations, right? Seawater is 28, and we saw that, you know, most fluids go to approach 0. So here we have end member hydrothermal fluids that have hundreds of millimoles of sulfate. These are the fluids that also have very high delta O18 numbers. These are delta O18 numbers you expect from a magmatic gas, and the hydrothermal vents that we sampled in the Manus Basin, about which I'll tell you a little bit more later on, they clearly show this magmatic water influence, but you can see that many other arc and backarc systems don't show that. So in general, the evidence that there is a lot of magmatic vapor coming into these systems, as well as CO2 and SO2, is scarce, and it's best seen in this Manus Basin example that I'll talk about more later. Carrying on, now we're looking at CO2 versus H2, hydrogen, and we see a complete decoupling here, completely different trends. And what you see is that the backarc systems, they are more gassy, more CO2, but lower hydrogen. So they are more oxidized. And the mid-ocean ridge systems are more reduced. They have higher hydrogen concentrations, although they are less gassy. There's one exception here. You see that there's actually this subgroup here of the arc systems where hydrogen is high. And these are hosted by barnenites, which are olivine-rich rocks. And how olivine manages to cook up hydrogen is a topic for another lecture. But I think most of you know that olivine-rich lithologies are wonderful in producing a lot of hydrogen. And this is what's shown here, looking at hydrogen versus silica. And this is fluid compositional data from ultramafic hosted sites. And you see they all have high hydrogen, but they all have silica concentrations that are significantly lower than the ones hosted in mafic rocks. Also, this tells us that the ultramafic basement cooks up fluids that are always reduced, always high hydrogen. All the felsic systems here are always oxidized. And the mafic hosted rock systems can be variably oxidized or reduced. There's actually a group here, it's very high in hydrogen. This is from the Cayman Trough, and this is due to very high temperature water rock reactions. So next we are plotting hydrogen versus hydrogen sulfide. And again, we see these two branches. And these two aqueous species can be related by this simple equation here. And what you see here is sulfur gas, okay? So if we are talking about, you know, how much of a gas do we have in a system, we express this in terms of fugacity. So basically, if you have a lot of hydrogen, but very little hydrogen sulfide, this tells you that the fluid represents a low sulfur fugacity. That's this trend. And this other trend here is the opposite, right? We must have a high sulfur fugacity to make a lot of hydrogen sulfide while we have little hydrogen. Okay, so we have these two trends. And here we see these other subgroups that I told you about before, that they represent very high temperature water rock reactions. So now let's think about what is controlling these two prominent trends that we see actually affecting most of the vent fluids. And you could say that for most of the vent fluids, the pressure temperature conditions in the root zone are around 500 bar, 400 degrees centigrade. And now we know there's iron and sulfur in there. And the magmatic rock has this phase called pyrrhotite, which is not a stoichiometric phase. So we give that a specific activity that is somewhat below 1. If you plug in these numbers and calculate what is the equilibrium constant for this reaction here that relates pyrrhotite, pyrite, hydrogen sulfide, and hydrogen, we find that the ratio of hydrogen and hydrogen sulfide is 10 to the minus 1.5. In other words, if these two minerals have a say, then the fluid has 32 times more hydrogen sulfide than hydrogen. And that's exactly what this slope here gives you. So here we are looking mostly at ultramafic rocks, and ultramafic rocks don't have pyrite initially. Instead, they have a lot of pendandite. And we know from studying these rocks petrographically that this pendandite reacts and forms pyrrhotite and this sulfide here, which is hazelwoodite, and also magnetite. So we're doing the same exercise and find an equation that relates these minerals and these two aqueous species that we've plotted, hydrogen sulfide and hydrogen. And we calculate the log K, and we appreciate the stoichiometry of the reaction to derive this relation here, which tells you that the ratio of hydrogen over hydrogen sulfide in this type of buffer situation or control situation is 16. So in other words, hydrogen concentration should be 16 times greater than hydrogen sulfide concentrations. And this is actually what we see in this trend. And if you look up the fluid compositional data for a system like Rainbow or Lagachev, you'll see exactly this. They have right around 16 millimoles hydrogen dissolved, and they all have around 1 millimole hydrogen sulfide. Okay, this is low sulfur fugacity, and this is high sulfur fugacity. All these ones down here have something to do with pyrite. These ones don't, because pyrite is a high sulfur fugacity phase. So this gets me to the next section of my lecture, where I'll be showing you phase diagrams, and it's just going to be the same one over and over again. And what it's plotted here is the log activity of hydrogen plotted versus log activity of hydrogen sulfide. And this is basically the same as looking at fugacity diagram for oxygen and sulfur, as I'll show you a little bit later. And but this type of diagram, which I think Bill Siegfried invented or at least introduced to the community, is very helpful, I think. Here's basically where I'm showing you that fluids with constant sulfur fugacity, right? They should plot along one-to-one line here. So that's the isopotential here for sulfur gas. And you could look at this diagram, and then of course here you look at hydrogen concentration, which is telling you something about oxygen fugacity. And you can convert this then into a fugacity diagram, where the isopotential here will be for H2S activity, okay? And here it's for sulfur gas fugacity. What's a bit tricky is how we convert between concentrations, activities, and fugacities, but there's some theoretical papers that help you do this. So why would we do this? Why do we care? It provides us with an opportunity, and I think Kawasumi and Chiba were the first ones to really go down this alley a good amount to link the oxidation and sulfidation state of the fluids with mineral compositions. And here's an example where I just contoured the iron isopleth, iron and sphalerite isopleth onto this diagram. And you can see that if your fluid is has a high sulfur fugacity, then the sphalerites should be low in iron And if it's a low sulfur fugacity fluid, then it should be high in iron. Okay. Or you could look at it in terms of redox and say oxidized fluids, low iron, reduced fluids, high iron in the sphalerite. Okay. And this then allows you, if you can manage to convert between gas fugacities and activities of dissolved species, you can really make full use of all these experimental studies from the 1960s and 70s, where the experimentalists controlled gas fugacities. So there's a wealth of data that we haven't really unlocked for our seafloor hydrothermal studies. And I think this is a development that is now started. I've been talking about arc and backarc systems. They are particular because there you have another species present in abundance, as we saw before, which is sulfur dioxide gas. So we could have the sulfur dioxide gas react with hydrogen and make hydrogen sulfide, which is this reaction here. You can see the stoichiometry gives you a slope like this. And what you have then, if the sulfur dioxide fugacity goes up, it drives the system in this direction here. See, well within the pyrite field. And actually, if we contour on this plot where elemental sulfur, which of course at these temperatures will be liquid, is stable, you could see that by fluxing sulfur dioxide into the system, you can get elemental sulfur stable. Okay, so we talked about phase separation. Now we talked about magmatic gases. So let's have a quick look at how boiling, so subcritical phase separation, affects the content of dissolved gases. And this is actually something we can calculate thanks to Drummond and Omoto. And I've done this here, keeping temperature and pressure constant and just driving off water. And you see that you lose hydrogen more quickly than you lose hydrogen sulfide. These differences are not very pronounced when you're close to the critical point, but if you are boiling some distance from the critical point, then you can see that boiling is a quite efficient mechanism to remove these gases and also to fractionate between the gases. And if you remember what I was showing you 10 minutes ago, these ratios of these two gases have something to do with sulfur fugacity. So this boiling mechanism is actually providing you with another way to increase the sulfur fugacity in your system. Again, which would help you make pyrite and perhaps even elemental sulfur. The GEMS modeling tool allows you to actually keep track of how the dissolved gas contents will co-evolve during boiling. Here you see following the two-phase curve in this temperature pressure stretch here, we can use the code to calculate how the densities will evolve and how the gas concentrations in the liquid phase will evolve. And you see that, again, you get this dramatic drop in hydrogen and much less pronounced drops in CO2 and hydrogen sulfide. Okay, and then we can contour these trends onto our phase diagram, where we can, of course, plot the compositions of fluids, and this would be a very reduced fluid, where you see boiling should not really affect the phase relations in the hydrothermal precipitates that much. But if you're down here, if you are looking at a fluid that is already quite high in sulfur fugacity, boiling, you see, we actually force the system to undergo a sequence of changes in mineralogy, right? See, from chalcopyrite, bornite to cobalite within the pyrite field, and then perhaps later crossing into the hematite field. Okay, How am I doing in terms of time? Oh, not too much time left, but I want to talk a little bit about the metals, because you may have asked yourself, well, why are we looking at gas species when we look at metal sulfides? We could do the same for the metals, and this is from Paul Traddock's thesis work, showing that you can, plot, construct similar diagrams using the concentrations of dissolved metals. But doing the metals is very tricky, and this is what's shown in this diagram. Perhaps, iron and manganese are not as much affected by it, but you do form metal sulfide precipitates in the bottle, and it requires careful work to redissolve all these particles and reestablish basically the concentrations of these base metals that were present in the fluid prior to sampling. So I have a few slides left about the case study. I'll do it very quick, and then I may skip some of the last two. But this is the area of the case study in the Bismarck Sea. This is the Manus Basin, and we will be quickly going to this volcano here, North Sioux, which is part of the Sioux-Sioux system, and then we have another quick look here at the Manus system on the Poal Ridge. We've been to North Sioux twice, in 2006 and in 2011, and when we came there in 11, we switched on the parasound system of the ship, and we saw this huge gas flare. And when we dove to the place where the gas flare comes from, this is what we saw. Lots of liquid sulfur, lots of liquid CO2 being issued from these systems. And in 2006, we sampled these fluids, and this is what they looked like. This is from Jeff Seawald's GCA paper. You can see that all the dissolved cations here go to zero. So the end member here has no sodium, no magnesium, etc. It does have some chlorine, which is likely then HCl. And it has these very high sulfate concentrations. And we can't be sure that all these acid sulfate fluids have zero magnesium end members, but because of these correlations here, for this particular fluid, we assumed a magnesium end member, a zero magnesium end member. And when we do that, then we can calculate the fumarole temperatures, which we've done here, conserving enthalpy, and we get these fumarole gas temperatures between 600 and 800 degrees C. Okay, so basically these acid sulfate vents are a completely different class of hydrothermal vent. They are different physically because what's providing the heat is this magmatic gas that is, at least in this case, rich in water, sulfur dioxide, and CO2, and that provides heat that will, heat up the seawater that is logging the pore space in the flank of the volcano. But looking at strontium isotope, for example, we can tell that there's very little fluid rock interaction that was going on in the system. It has a very high gas flux, means that the rocks in the upflow zone are completely altered. There's no buffering, there's no exchange in, between fresh rocks and fluid that you have in these parts of the system. So the chemistry of these acid sulfate fluids hence is radically different. And I'm stressing this because I don't think all that many people have read Jeff's paper, and because I keep noticing that when we get papers out of review that, some people are not familiar with this concept that we have this other class of, deep sea hydrothermal vent system that is fundamentally different. And that's why I included this slide here. This other last topic that I have in my lecture and actually the time is up, so I'll make this super short. I'm looking at different parts of these Manus vent site on the Poal Ridge, and we are looking at, again, salt and gas, and we see that the gases all show different things, right? CO2 shows what you would expect. The low chlorinity fluid has a lot more CO2. So we see that it's affected by magma degassing. We see it's affected by phase separation. Hydrogen doesn't show this at all. In fact, hydrogen appears to be highly reactive and insensitive to phase separation and magma degassing. And hydrogen sulfide is kind of in between. And again, this goes back to the speciation changes in the degassing fluids, and we would expect to have lowest hydrogen and highest CO2 at these higher pressures. A quick look at the metals, and just zinc, gold, and silver plotted versus salt, temperature, and hydrogen sulfide gas. And again, you would think, you know, the metals should be better behaved, right? Because it is chlorinity, it is temperature, it is abundance of sulfide that controls the solubility of metals in theory. But instead, what we see is mostly shotgun plots and things we were not expecting at all. Zinc is chloride complex, right? But we have this big group here, Roman ruins, where actually the low chlorinity fluids have high zinc concentrations. Okay, so we could spend more time looking at these in more detail, but I want to wrap things up and make a pitch for this reaction path modeling that allows you to combine all the data we have for salt, gas, and metals. And what we do here is we just mix. We take one of these fluid samples that we collected at this Roman ruin site in Manus, and just mix it with seawater, because this is what's going on when the primary sulfides first form. And you see you form sulfides, but you also form a lot of sulfate. So this is basically what, you know, in a very simplistic model, what the mound material that you first make should look like. And there is a big sulfide mound at Roman ruins. If you have a big sulfide mound, you also have what we call zone refining and supergenius enrichment, because fluids will come into the mound from below and seawater gets entrained. So in this step here, I'm mixing seawater with an end member hydrothermal fluid to bring the temperature to 275 degrees C. And you see what's happening on the way is the fluids become enriched in zinc, arsenic, lead, antimony, silver, and gold. But copper and iron don't go up. Instead, they drop a little bit. What is happening to the sulfide that we were just making, the sulfide-sulfate mound? You see that the sulfate in the course of the reaction actually disappears and completely vanishes, and the sulfide contents go up, in particular that of pyrite. Okay, you can also see that now you have gold precipitating at the first time, but we are not done, because there's actually that what we are doing next is we stimulate what should get precipitated in the top section of the mound, right? Because there's now the mound is undergoing zone refining. So we keep mixing this fluid from the previous step with seawater, which is what you would expect to happen at the top of the mound. And then we look at how that will affect the composition of the top section of the mound. And this is what the model suggests will happen. You can see that copper, for example, just goes a little bit up, but zinc goes up a whole lot. Lead also. Iron, not so much. Arsenic goes up, and then antimony and silver also go up, and gold goes up. And eventually, the gold concentration in the top section of the mound is predicted to be an order of magnitude higher than what we had in the initial precipitate. Okay, and this is how the fluid drops all the zinc and lead and arsenic, but not so much the iron. And that causes the top section of the mound to be this zinc, silver, gold, lead rich. zone that we actually observe in these deposits. Okay, thanks guys for your interest, for your patience. I'm sorry I went a little long, and I'd be happy to answer questions you may have. This is just a brief summary, and I'd like to actually finish with acknowledging all the help I got by these colleagues that are listed here and the funding agencies.